Hi everybody, welcome to our next topic in grade 12 physics. Hopefully today won't be too challenging or long. What we want to do today is kind of look at some of the ideas you've covered before in grade 11, this idea of waves and what happens when they hit boundary. And we're also going to look at building on some of the ideas from last time in light, and also going back to way back in grade 10 when you did geometric optics, just a little bit. Don't get too freaked out. But again, hopefully it won't be too difficult. We just want to review some of the things that happens when light hits a boundary. And again, what I mean by boundary, we'll talk about it in a second, but when light goes from one substance to another. But before we do that, let's quickly just talk again about what light is. So remember that light, we can model it as a wave, and a wave of a changing electric field and magnetic field. And one of the most important quantities about this wave is then the length of it, or its wavelength, which we represent with the Greek letter lambda. And what makes one color of light or one type of electromagnetic wave different from another is just the length of that wave, or the wavelength, which we can also then write as the frequency, since all waves are linked by this sort of universal wave equation. C equals lambda f, C being the speed of light in a vacuum, and this is where we kind of want to branch off of from today. And just for reference, here are some the visible spectrum, what kind of wavelengths and frequencies we can see for the colors that we see. All right, so with that in mind, let's see what happens when light actually hits something. So remember that really there's only three sorts of things that can happen when light hits a boundary. But before we talk about what the heck um, could happen, let's figure out what the heck a boundary is. And so a boundary in physics is just a change in medium. So when light changes from one substance to another, so let's say it was traveling in, let's say, water, and then it enters the air, we say that water has hit a boundary, or it's gone through an interface. And so another example would be here the air glass boundary between the or the light shining in through the window. So the air glass boundary would also be the interface between the air and the glass. And we're going to say that again, light has hit a boundary. And what happens to that wave? Well, again, when we're talking about what happens to the wave, what we really mean is what happens to the energy, because that wave is actually a form of energy. And again, this is where your recollection of grade 11 physics comes in, that really only three things can occur to that energy of that wave. It can either be reflected, it can be transmitted, or it can be absorbed. And what's actually going to happen depends on the nature of the materials, the interactions themselves, what sort of things are happening. But one or some of all of those three things will happen whenever a wave, or in this case light, hits a boundary or interface. Um, so just again, a little animation here. Remember some of the stuff from grade 11. Depending on what the interface, so this here would be the interface or the boundary, what it looks like and what its properties are, that's going to change the way that the light is actually, or the wave is reflected off of it. So for instance, the first case here, the wave is reflected off in one sort of orientation. You can see it's coming in with a positive amplitude and leaving with a negative amplitude. But in the second case, the wave is coming in with a positive amplitude and leaving with a positive amplitude again. So there's certainly something different there. And the same thing happens with light, since light behaves as a wave. But what's actually different about these two interfaces in this case with light is the speed. And so we've got to talk a little bit today, before we get too far, into this idea of the speed of light. And we know that, of course, in a vacuum, all light travels at the same speed, c, that universal constant, again, c constant, somewhere in the neighborhood of 3 times 10 to the power of 8 meters per second, so incredibly fast. Um, but one of the neat things is, as we'll get to in a second here, light actually travels at different speeds in different substances. So in a vacuum, light travels at that speed c, the speed of light. But because light is actually traveling as an electromagnetic wave, these substances it's traveling in actually have magnetic and electric properties themselves, and so the light will interact with those materials. And when those electric and magnetic fields interact with the material, the speed, or the how quickly that field can change will also then determine how quickly that light can travel. So the takeaway from that is that different materials will let light travel through it at different speeds. And we're going to call that quantity of how much slower light travels in different media, we're going to call that the refractive index. And again, you should have talked about this in grade 10 science. Um, and the defining sort of expression for refractive index is just n, which is refractive index, is c over v. N is refractive index, already said there. C is the speed of light, and v is just the speed of light in that material. So we're actually taking one speeding and dividing it by another. So n is going to be a unitless number. And so it's just a ratio of how much slower light is in that material compared to the speed of light in a vacuum. So to give you some examples, in a vacuum, it is exactly 1 because we're taking C dividing it by C. So C over C is exactly 1. In air, it is almost exactly 1. But as we get into some other materials, like let's say ice or liquid water, we're getting quite a far distance away from 1. So what this means is light travels at about a third, or like say 30% slower in water than it does in a vacuum. And we could actually get the speed if we just shove it into this expression here. And one thing we can always we can be sure of is that n should be greater than 1 since it's a ratio. And if n were less than 1, that would mean v would need to be larger than c. And again, conventional physics says we can't actually do that. And so we're going to have that value n being greater than 1. Okay, so there is kind of how we can bring speed into this. So let's now go back and say, well, why do we care? Well, because speed is going to determine what happens. Well, part of what happens when light bounces off or hits something. So let's go back now and visit our sort of 3 cases. We'll start with the 2 maybe less exciting ones. Probably the least exciting is absorption. But again, you definitely talked about this in grade 10 science. But absorption is the transfer of energy from light to another form of energy, and often that form of energy is going to be thermal. We might also talk about things like converting into electrical energy, like in solar panels. Um, but for this example, it's again, in every example, if you wear black outside in the sun, then you know that the shirt will be warmer than if you wear a white shirt, and that's just because again the black shirt tends to absorb the incoming solar radiation, and that energy is not reflected back; it's absorbed, and that extra energy then goes to thermal energy of the shirt, whereas the white shirt would reflect that energy back, and it doesn't convert that energy into thermal. And again, so different substances are going to absorb different amounts of energy depending on all sorts of different factors. And we can talk a little bit about this, but it's kind of that you kind of did a lot of that in grade 10. So we're going to kind of leave absorption a little bit. We'll spend a little bit of time on reflection because some interesting things happen, mostly whether or not the wave is inverted. But when light hits a boundary, the wave is reflected back. And again, something else that you should remember from grade 10 science is that's angle of incidence is equal to the angle of reflection. Reflection. So again, I'll leave it kind of at that for right now because again, that's a grade 10 kind of topic. But the one thing that's kind of cool, we'll talk a little bit about this when we explain some other cool phenomena, is that sometimes the wave is inverted. That has to do with, again, with what the refractive indices are of these two materials. So whether it's going from a high end to a low end or low end to high end, and what that's going to do to the reflected wave. So again, these two I said are probably not the most exciting, but we certainly will talk more about reflection later on. But one of the neat ones is transmission. And why I think that's probably the neatest one is because when light actually goes from one substance to another, it bends. And that's kind of strange at first glance. That so light travels in straight lines, we see it all the time, but when it goes into something else, it's actually going to change its direction. And to kind of explain why, I think the most obvious or an easy to explain way is to think about a wave keeping up with itself. So if we imagine here, I have 3 incoming rays, 1, 2, and 3. And each ray is just part of a wave front. So you can imagine that this is like an incoming water wave, let's say. Um, and so each ray is just representing like one sort of section of the wave. And as each ray comes in, well, it's just part of a whole front. And so as it hits here, well, you'd think that it has to keep up with its same front. So let's see, I'm not doing a very good job explaining this. Let me try again. So it comes in as one solid wavefront. And when it leaves, it has to again be one solid wavefront. So how could that possibly work if it's going to be hitting at different times? And the only way to make that work is if, as it's coming in, the wavefront itself actually bends at the interface. And so what we're actually seeing here is as each ray comes in, each ray has to bend. And it has to bend so that wavefront itself can be continuous. It doesn't break off and then rejoin up with itself. And so in the end, we're going to have each wavefront having a bend in the middle because each ray will bend. And what's actually going to happen is the ray will bend toward the normal when the wavefront slows down. So you can see the wavefront here is traveling fast, and now it's going to be going slower. You can see that because the wavefronts here are closer together than the wavefronts here. So the lambda is shorter here than here, so we know they have to be traveling slower. Um, and so we can actually get an expression using geometry for this angle theta 1 and theta 2. And we actually don't have to do it. Somebody's done it for us. And we come up with Snell's law, which again should be something you've seen in grade 10 science. So this just tells us how much light will bend when it travels from one substance to another based on its refractive index. And so we see this all the time. This is really super important when things are making like eyeglasses or telescopes or fiber optic cables. These sorts of expressions are super important because we have to make sure the light bends the right amount. And you probably are sick to death from drawing ray diagrams from grade 10. And don't worry, we don't have to draw a whole lot of them for right now. And we're going to leave Snell's law more or less right about here. But there is one kind of thing we want to do with it before we leave it. And you probably didn't talk about this too much in grade 10. Um, but it has to do with this refractive index isn't quite complete. And what I mean by that is refractive index actually is frequency dependent. And I think this is pretty cool. So if you look at this kind of graph here, let's examine this graph for a second. So what it is, let's just look at maybe plexiglass. So based on wavelength, so 400, 500, 600, 700, so this is almost the entire visible spectrum here. The index of refraction for plexiglass goes from around 1.5, I don't know, '05, say 1.505, all the way down to 1.490, somewhere in that ballpark. So what that means is when light travels, if white light is shone into plexiglass, the blue light will bend a different amount than the red light will. So what that means is, as it's kind of shown in this picture here, they'll end up coming out in different locations. So you shine a red and a blue light in together, they're both originally together on the same path, but they're going to come out along different paths. And so we call this effect dispersion. And so rainbows are actually partially due to this. Whenever you see a prism kind of breaking a white light into its colors, kind of like this is due to dispersion. And this is, again, I think, a really cool effect of Snell's law and refraction. So we'll talk a little more about this a little bit later on and how this is important. So I think I'm going to leave it there for right now. And I think that's hopefully not a too terrible difficult topic for today. Most of your review of stuff you've already got, and that's it out of me. So I hope this is makes sense, and I'll see everybody in class tomorrow. Have a good night, guys.